So in this video, we're going to be doing some examples of determining whether a series converges or diverges. My index in all of these are n, and I'm summing them to infinity because that's where my index starts is not of particular importance as long as the sequence is defined for all values of n. So in this case, n needs to start from 1, otherwise I'd have a 0 over 0 error. And then for example in the series, n needs to start from 2, otherwise I have a divide by 0 error, and so on. So in this particular case, we would use the comparison test and say that this is greater than the sum of 1 over n. And since we know that 1 over n is the harmonic series and diverges, we can say that this series diverges. So we would use the comparison test. For this series, we would also use would I use the comparison test? Yes, actually, in this series, I would also use the comparison test. Since I know that ln of n is less than n, I can say that 1 over ln of n is greater than sum of 1 over n. And so this also diverges by the comparison test. And so therefore, diverges by comparison. When we encounter a polynomial, or 1 is a polynomial over a polynomial, usually we can use the limit comparison test, and the limit we would compare it to would be the highest power of our numerator, which in this case is 1. Limit as n goes to infinity of bn over an is equal to limit as n goes to infinity. The highest power of our numerator is 1, and the highest power of our denominator is actually 2 over 3, n to the power of 2 over 3, and 1 over n squared plus 1. And so, as we can see, as n goes to infinity, this limit actually goes to 1, which means that this series has the same behavior as this series. This series we can see as a p-series where p is less than 1, which means the series diverges by limit comparison test. With this series, because I see there's a factorial, I'm going to use the ratio test. The ratio test is super effective for any series with a factorial because of the nature of a factorial. So in this case, we have n plus 1 squared over n squared times n factorial over n plus 1 factorial. This reduces to the limit as n goes to infinity of n plus 1 squared over n squared is equal to 1 for large values of n, because as n gets very large, the plus 1 becomes less and less relevant. This is equal to 1. N factorial over n plus 1 factorial is equal to 1 over n plus 1, because n plus 1 factorial is equal to n plus 1 times n minus 1, and so on all the way until 1. And as n goes to infinity here, this equals to 0. And since my limit is less than 1, this converges by ratio test. In our next example, we have some lns. And so the rule of thumb for lns is to use the integral test, because when we use the integral test, so let's integrate from 1 over ln n, or not n, I guess, because now it's a continuous function, ln n to the 1000, and we're going to say that, dx. And we're integrating it from the boundary to infinity. some constant to infinity. In this instance, we can let u equal to ln of x. So eu du would equal to dx. Actually, I should explain how I got that. So if u equals to ln of x, then du equals 1 over dx. Okay, 1 over x dx. 1 over x dx. And so x du equals to dx. And if we isolate for x here, we get that e to the u is equal to x, which is how we get eu du equals to dx, which means this is equal to the integral of ln of k to infinity, because ln of infinity is still infinity, which is why the divergence test doesn't work here. And we'd have e to the u over u to the 1000 du. I don't know about you, but I don't know how to integrate this. And since I don't know how to integrate this, what I'm going to do instead is, because I know that a series will converge if its integral converges, and alternatively I know also that if a integral converges, then its series will converge too. So now instead of evaluating this integral, I'm going to convert it back to a series from some index to infinity equals some index, let's call it b to infinity, of e to the n to the 10,000 or 1,000. And by the divergence test, so let me apply my divergence test actually. Limit as n goes to infinity of e to the n over n to the 1,000. Now this may not be completely obvious, but if we use L'Hopital's rule 1,000 times, eventually we'll get a constant in the bottom, and our numerator will still be e to the n. So we have e to the infinite power over some constant, which means, well, it's not equal to 0, which means that the series will diverge. So diverges by integral and divergence test. For the next series, again, since I have a polynomial over polynomial, I'm going to use the limit comparison, and then goes to infinity, of the highest power in the numerator, which is n squared, over the highest power of the denominator, which is n cubed, over n squared over n cubed plus 1. This is equal to n squared and n squared cancel out, and we have n cubed plus 1 over n cubed, and this is equal to 1. Since this is equal to 1, we know that this series behaves the same as this series, and this series is equivalent to 1 over n, because I divide top and bottom by n squared, and this is the harmonic series, or the p series, which we know diverges. So this series diverges by our limit comparison test.